The broadcast is...
Okay, so today is the second lesson within a series that we are doing every Thursday for the next, let's see, now it's 9 more weeks of this. Today I will be talking about modeling temperature and radiation and wind speed. However, in this model or in this presentation, the methods I'll show are not well. There's one method actually. I don't have multiple methods to show, and it may not necessarily be applicable, but I just want you to see what we have in our library, and also talk about different ways to include it for your models. So the reason I'm bringing all of this up is because next week we will talk about calculating evaporation. So for example, on a lake water surface, or also evapotranspiration if you're calculating water demands. And to get those kinds of outputs, you might need temperature, radiation, wind speed. You also might need percent of, or the amount of sunshine or duration of sunshine within a day, depending on the method that you're using. But before we get to that point, I just wanted to talk a little bit about how you might incorporate this in your model. But before we talk about that, we should first see, do you need it? Is it necessary to include temperature in your model? If you're doing, for example, a water balance and you need to incorporate evaporation, but let's say it's a very small, let's say evaporation has a small impact on the overall results of your model, then perhaps going to the effort of temperature to drive evaporation is not very efficient use of your time and resources. So just keep that in mind. But if evaporation or calculating water demands from ET rates, for example, if those things are driving your model or very important, then you probably want to look at this. Also, last week I talked about precip, and I walked through this model we're looking at right now too. And it's some of the concepts were very similar to what we talked about before, and some of them I'll just skip over. So for example, you might want to just have a table of monthly values of average temperature, or any of the other inputs, and you would use the same methods that I talked about last week. And by the way, if you were not present last week, you can go back to our archive and watch the video and look at the models that we talked about. And I will be recording this one as well and also posting it. Okay, so in this model, what we're looking at is actually just one realization. And the reason we know that is if you look at the bottom bar in the green area, it says 1 right here next to the realization icon, indicating that only 1 has been run. And also, you might be somewhat new to embedded charts. There are 3 embedded charts here. If you double click on one, it'll look just like a regular chart that you've opened in the past, except for the fact that you cannot access the properties page or dialog here. But you can zoom just like before, holding control down and dragging a window. But if you double click it to close it, you see it goes right back to where it was. And these are the default settings that the author of the model can set for you. But you can always double click, and you can also change some aspects of what you see in the model. So for example, I could remove, well, I need the full GoldSim to do this kind of thing. But if you were just using the player, then it would pretty much just be here. You can view this, but there is one more thing the end user will be able to do, and that is if there are multiple realizations, they could look at a statistic, for example, right here, which I'll show you in a second. But this model, it uses some constants, some parameters, and not very many, to derive the temperature values that you see here in the red and the blue. And then it only requires 3 inputs, which are down here at the bottom of this table, to derive the the solar radiation, which you see here in red. Also, importantly, on the solar radiation, it is a function somewhat of rainfall. So if it's a rainy day, then you should typically see a correlation somewhat of radiation dropping when it is raining. Typically, not always, but you would tend to see that correlation because that correlation is built in to the model. Okay. Oh, you would also see that with temperature. You would see a drop in temperature slightly on days that it's raining. Okay. Let's see what else. Okay, so last week we talked about how to derive the rainfall using this table of information here, but for the temperature, like I said, all you need are these constants. But important to note, these constants come from evaluating time series records of historic temperature values. So it's not like we just randomly came up with these numbers or we have some sort of defaults or something. No, we came up with these by doing an analysis of historic records. So it is based on the historic record. Also, it's based on the site location, actually the latitude of the site that you're measuring the temperature at. Okay, so let me just talk a little bit about how that's generated. If I go into the model, then what we talked about last week was the precipitation, but over here on the temperature and the radiation, we have a thing called the Fourier function that's driving one of the parameters to find the max and min daily temperatures over time, which you can see here. It's really just coming up with a factor that's multiplied over time. Okay, so that probably didn't make very much sense what I just showed you, but let me just walk through the Fourier function. So, and by the way, while I'm doing this, just note, this is all just GoldSim being translated, I guess you could say, or we looked at the Fortran code and developed the equivalent functionality in GoldSim, minus some of the things that you just kind of have to do in a programming language, like for example, setting up different types of results. For example, there might be some summary results that the Fortran code provides, but GoldSim does all of that in its interface. So a lot of that kind of code is skipped. But that's really just about post-processing, for example. Also, there was a bunch of logic in there for dealing with calendar time. Obviously, since GoldSim is a dynamic simulator, we don't have to worry about that because it's built in. And so there were some things that were easier, and there were some other things that might be more compact in a programming language. So for example, in the Fourier function, we have these loops that we have to do. And in the code, they're really just a for loop that you just can refer to, as they're just a subroutine essentially. And there's a for loop in there. But in GoldSim, to do a for loop or the equivalent of one in which we repeat calculations at any point in time, or on each time step, for example, then we would need a looping container. And so this looping container just loops for 3 times. So you put in logic here that says loop until the loop count is equal or greater than or equal to 3. That's how you do a loop of 3. And the reason it does it is because there is a, well, it goes even deeper, but there's a matrix that it's iterating over that needs to do it 3 times. And on each time, it inputs some random numbers. And the nice thing about these stochastic elements is that you can trigger them anytime you want, in this case, on the loop count. So each time we iterate, if you imagine a for loop, each time we iterate over it, we're going to pick a new random number. And that's what it's doing in Fortran to come up with these. Okay, so then we get we end up with these factors essentially that are applied then to these temperature amounts using some other factors based on the inputs that we provide it. So and if you look at some of these scripts, you can see there's quite a bit going on here. But what we did when we built this was put in some results from the documentation of the Fortran and compare it to the GoldSim results. And then we also compare it to observed results. So when you first download this model, you could always go in here and you could look at, in the verification, how close are we? And it should still be matching fairly closely there. But anyway, back to the temperature. So essentially what it does is it comes up with some factors, but it's also, you can see here there's an influence line, a green influence line. And the reason it's green, just as a review, is because it's a Boolean output that is going from there over. And this is the Boolean that's telling us whether or not it's a wet day or not. And you can also follow this, by the way, just by, you can double click on the line and find out where it's going to, and it's going into here. And so there's probably an if statement in here that says if it's raining, right here, if it's raining, use these values instead. So that's what it's saying to do. And that's where the correlation between a rainy day and the temperature comes into play. Okay, so there's also a way to do a little bit of a correction on the temperature that you end up with. So that can be done as well. And essentially this will result in daily temperature values. Note, the model is not currently set up for a different time step, hourly or monthly, for example. But could you do it? Yes, you probably could, but I'm just not sure. You probably need to change the precip generator a little bit. The precip generator has probability values that are assuming it's a 1 day, but you could adjust those probability values for 1 hour. I imagine if it's an hourly time step, then your and I'm talking about these probability values here. These just as a review from last week, these probability values are the probability of today being wet if yesterday was wet. And this next one is probability of today being wet if yesterday was dry. Okay, so those two. These would be different numbers, I would think, if it's an hourly time step. I think the PWW numbers would be higher, and because I mean, it's a shorter time step, so it would stay raining longer, or it would be raining more time steps in a row. And so I think that would be, I think those would be higher numbers. I don't know about these numbers, maybe these two. Okay, so you can probably change the time step, but it's not as simple as just changing it in the simulation settings and running it. Not yet. We'd have to do some more work to it to allow it to just seamlessly change like that. But you can change the units. So if your temperature units are in Celsius, then when you generate your inputs, you'd want to do that in Celsius, and then you'd also want to run this model in metric as well. Okay, so why would we want to use this model? You would benefit most from this model if you need to do future projections that don't only rely on historic records. Maybe you want to look at some possibilities that vary from what we've seen in the past, but not in an unrealistic way, because this model will generate forecast simulations that are based on the historic record. So they won't be too far off of what you have observed. The other nice thing about this model is, let's say you were also looking at running a very long-term simulation, let's say 50 years, and you want to adjust some of the average numbers, some of these constants. So for example, the mean max temperature, perhaps you want that to slowly increase over time, over the years, then you could just simply swap that number out, this one, with an output of another part of your model that might be projecting average temperatures, for example. You can also adjust any of these other numbers in a similar way, the amplitude, the coefficient of variation, etc. Now these numbers, if you're wondering where did these come from, that's a good question. They came from the WGen PAR model, which looks like this. And both of these can be downloaded from our website. But in this model, all you have to do is set up the time series just by clicking these and copy pasting into here. Also keep in mind that you will be specifying the unit type, whether it's metric or English. So make sure you keep that in mind when you paste those numbers. But anyway, you put the temperature values here, radiation, if you have it, and of course the latitude. With all of those inputs then, just make sure you set the settings so that the start year and end year do not go beyond what the time series have. And it's the lowest common denominator of all these time series, by the way. If you, by chance, have only a small set of years for, let's say, temperature, let's say 10 years, then you would run this whole thing for 10 years. But if you had more years of record for, let's say, precip, then you could rerun this model with all the precip in there, running all the years. And then just make sure you copy the results from those individual runs over to WGen. But the point is, you fill in the data, you change the settings, you choose the unit type and run it. And then GoldSim will export those results to Excel. And the only reason that's done is just for convenience, so that you can copy and paste those values over to the WGen model. And another option is, let's see, is there another option? I think you can select now and copy. Yeah, I think we can copy and paste now in these grids. So you could also just do that instead of using Excel. But once these are generated, then you can run WGen with these. One thing to note though is, if you had, maybe you have climate change scenario type temperature time series, maybe they've been adjusted already. And then what you could do is bring those in, and they would give you an adjusted value here. So then in your model, you could say, well, there's so much duration between those two values. We're going to model a projection of average temperature and these other input parameters. You could model it, and then have those inputs override in WGen. Okay, so let me explain what I mean by that. What I'm talking about is changing these constant values to be an output of some little function you put in the model. So to do that, first we need to know, where is this number? And that's easy to find. Go to edit mode, and then change your dashboard to not be active. Okay, you know it's not active because you see these droplets turn dark gray. When it is active, then you can interact with the model, but when it's not active, then you cannot. But you can double click on them and see their properties. So in this case, mean of Tmax, you can see right here, is linked to this element called TXMD underscore. In fact, you could even click on it and see its value. Okay, but anyway, TXMD underscore, that's easy to find. We can just do a search, and there it's already there. We don't need to search descriptions. And then find, and here is the input. Okay, so when we open it, you can see it's telling us it's already connected to a dashboard. You can go to the dashboard and where it's connected by clicking on this. So you can't really just change this right out, but we don't want to do that anyway. We would probably just add a new expression element here that's an output of temperature changing, and then link it up to this. Okay, so that would be pretty easy to do. And we could do the same thing with perhaps with radiation. Okay, so with that, I think I'll stop there. There are some other models to simulate temperature, do forecasting of temperature. So for example, this model was already shared with the group. I think I did a webinar a while back on it, but this one is a way to do a forecast. I think it's this one. Okay, so this model, what it does is it will get the temperature forecast for the next 7 days using the web data interface, the API that the National Weather Service provides. And so right now we're looking at a run. Well, this was done a while ago. So let me edit this and let's look at the, okay, so we need to update, let's update this to 9:10. Oh, I didn't change that. 9, 10. And then we'll change this to 7 days. There we go. And we check the box to enable a web download. And so what this model does is simulation start day 10 is not the same as the forecast day. Yeah, I have a bunch of error messages going on. It looks like it's expecting, hold on, let me look at the forecast day. Let's see here, simulation start time, 9:10. Oh, I see. Okay. There's a run property that you probably don't know about, and it's called now right here. For some reason this didn't update, but that's supposed to be your computer's clock time when you run the model. So now it probably won't give us an error. I probably should fix that. Let's see if this works. There we go. Okay, so no errors that time. But this is the forecast, the temperature forecast for this latitude and this longitude. And you can see that the maximum is going down a bit and the minimum is pretty constant. But there's this range you can see that's getting wider and wider over time. And to be honest, I'm not sure where this location is. This might be Seattle. It kind of looks like the temperatures we'd be seeing in Seattle, so I bet it is. We could check with these numbers here. But anyway, the reason this band is getting larger is because, well, today's temperature is obvious. So we know that, and so that we wouldn't have a width of a band there unless it was maybe early in the morning when we came up. No, I don't think so. I think this is going to be 0, but then it grows as you go forward. And the way I came up with that is this thing called temperature forecast accuracy. And they have this published on their website for both max and min for this particular site. And it's called mean absolute error that they publish on the website. And so I used these numbers to provide the range of uncertainty for the forecast to come up with that. Okay, so why am I showing you this? Well, this can be integrated with other parts of your model. For example, WGen, which we just talked about. You could incorporate that with this model and come up with a longer term temperature forecast, which would then help you with maybe, for example, rainfall runoff modeling or evaporation if it's a big important thing in your model, that kind of thing. And okay, so there's another model. I can't remember if this is the one, but let me see. Yeah, this is the one. So in this model, we have the same forecast. I just copied and pasted it in here. But then in addition, we have the WGen. So if you look at the inside of the model, you'll see we have the forecast. That's what we just looked at. And then WGen. And they're tied together with a transition inside. Not here. I'd put a transition somewhere. Well, I know I did it. Well, I'm not exactly sure where I came up with it, but it's there. It looks like, well, I don't know. But I'll have to find it after. I don't want to spend too much time looking for it, but it's there. There's a transition period, and it's really simple, actually. That's probably why I didn't find it, because all it does is it looks at as we transition. Oh, by the way, you can change the duration of the transition. But as we transition from the forecast into totally being, a stochastic simulator, then we need some way to gradually transition, or not so gradually. If you don't want, you can move the slider to be less time, but it needs to be at least 1 day to transition. But essentially what it does is it says, okay, here's your forecast. It has this bandwidth, this much error. And then over here, we have the full WGen totally stochastic synthetic generated temperature. And in between, we have to change slowly. And so what it does is it says, put on the first day of the transition, put the weight mostly on what you just saw in the forecast, and then as you move to the right, then slowly put more weight on what WGen simulates, and then connect it. So that's what it's doing. And it's not a it's a rule of thumb, I guess you could say, just a way to ease the transition, because WGen is calculating a temperature just based on the latitude. And so it's while it's realistic on an average basis, on an average of many years of records, it's not going to match, exactly with what what really happens, obviously. And so that's why we need some sort of transition into that area. Now, I realize there are other temperature models that you can gather information from that are longer than 7 days. So that might be something to look at too. But anyway, this is a tool that you can use the temperature information for in your WGen model. And okay, the last thing I want to talk about is the wind, a wind model. I have a model, but it's not physically based or anything. I didn't find anything in the time I was preparing for this to use as an actual model. But what I did do was look at a historic record time series and just analyzed it statistically to come up with means and standard deviation and probability distributions for each month, and then run that through a stochastic to generate approximately what we've seen in the time series records. And so in this way, it's a different kind of, I guess, model, you could say. But let me just explain how I came up with that. So we have a time series that runs from 1984 all the way down through 2017. And so what we want to do is develop what we need to understand. What is the range of possibility for wind speed each month. So we want to know about its distribution. We want to know, for example, the statistics, the mean and the standard deviation, for example. But we actually want to sample. We want to sample all the wind speeds for each of the months. And so we could probably set up some logic in here that would just automatically process that time series, but I didn't feel like I had enough time to work through that methodology. And so I just kind of brute force did it in Excel. So let me explain what I did. So I have this time series with these dates all the way from 1984 to 2017 or 18. But I need to categorize the months. I need to put them in, I need to collect and group these dates by months. And the reason I need to do that is because I want to do a lookup on the time series using realization. So here's what I mean. This main model is going to take the definition of this time series as an input. Then what it's going to do is it will just run all the day. It'll run through each of the days of the month. Let's just pick January, for example. It'll look at January and it'll sample the values from this time series each day of the month. Let's say 31 days. So it has 31 values, but then it will go to the next year following January and repeat it. And now that has 60 values that it's sampled. Then it will do it again the third year and it will get 90 samples, and on until it has whatever the total number of its approximately 30 times however many years we have a record, I think 33 years. And so that's the number of samples that we are collecting from the time series, if that makes sense. Okay, so how do we get the time series into the submodel to run? What you'll see with the time series is that it has two outputs. It has the main output, which is just its value at any given time. Then you also have the definition, which is the entire set all at once. That's what we want to pass into the submodel. So you go to the submodel interface, and then you hit the plus sign, and you refer to, if I do it now, you'll refer to not just the name of the time series, you'll open it up and refer to the definition. That's different. That's the entire series. Also, what we want to do is we want to, based on however many number of years we have in the time series, in our case, I think it's, like I said, 33 or something. Yeah, 33 years on record. Then you can set this submodel manually. You can tell it how many, not manually, sorry, actually automatically, you can tell it how many realizations to run. And that's being done here in the interface as well. You can see it up here at the top. That's defined with this icon. If you click this one, this is adding a run property to your submodel. In our case, number of realizations to run, which in our case is the number of years times the number of days in the month. Okay. Okay, so those are the inputs. Then the time on this submodel will be 0 time. It's a static calculation because we're just going to sample the time series at specific dates using Monte Carlo. If we go to the Monte Carlo tab, you see it's already defined as the number here. That's the number of realizations. And now let's talk about how we get those realizations to do a lookup. Okay, so we have a time series here. This is just linked. If you look at the data source, it says link to external. This means it's coming from the outside of the submodel. Coming in, you can go to the link tab and see the name. That's the wind time series definition that we were just looking at on the outside of the submodel. Okay, so that's the time series. It's just like any regular time series now that it's in here. And the only difference is that you can't look at the data here because it's linked to the output of another. Okay, the lookup table, this is the thing that's going to kind of seem crazy at first, but what it is, it's just a table of dates. And the dates, because it's a lookup table, have to be written in a numeric fashion. It's the same way you would see in Excel if you converted the date to a number. So these dates in the first column represent all the January dates all the way down. They're all the days in January for all the years on record, all the way to 2018. And then this February, March, April, etc. And the rows going down, these represent the number of realizations we're going to run. So on realization 1, we're going to return a date for this column that is in January, on the first day of January, for example. This next column is the first day in February, etc. Okay, so that's that table. We can then refer to that table to get a date value that then we feed into the time series function to return the value from the time series. That's how we do a lookup on this table. And so we can now, this is actually a vector of months. So we're doing this 12 times. We're repeating this calculation 12 times. The calculation is go to the time series and do a lookup on it. So we go to the time series and then we provide a date. And the date is going to be from this lookup table. And then we give it a realization number. Remember, that's the row going down. And on the first realization, it's a 1. And then we give it a month number, and that's defined as row because that's what we do in a vector constructor. And it's a vector of months. So row 1 is January, row 2 is February, and so forth. So this will build immediately. It will build a vector of time series values, which are the temperatures, sorry, not in this case, the wind speed, and then return it here as an output every time this runs Monte Carlo until when you finally finish running it, you can look at the distribution and it will show you a distribution of wind speeds for all the months. And you can see here that in January, the wind speed is quite low. And then if you look at the neighboring month, February, you'll see it's also quite low generally, but then you'll see it has some very rarely some high values. These are some of the important factors you'd want to include in your model of wind speed. You'd want to make sure you incorporate the fact that yes, there are some very windy days on average in February, for example. So with all of that being said, then what we can do is we can output or export those distributions for each of those months on the outside of the submodel. So if you go to the submodel and you look at the interface, you can see here are all the months. And for each of those, I've taken a final value distribution. That's one of the types of outputs you can output from a submodel that's doing Monte Carlo. It outputs the entire distribution. Now you cannot do it in a vector format, so unfortunately. So that means you have to refer to the index, the row of that vector, but that's okay. It was 12, so it's not that bad. Okay, so now with that being done, then you can build an array using a data element that refers to each of those months' values. And this might look like a lot of work to type all this in, but you don't have to do that if you use the concatenate function in Excel. So what I mean by that is, let's say you just type this first one. That would be a good idea. Type the first one. It's using our built-in special function that it'll return the mean of a probability distribution that you have in your model. In our case, the values for January. It's going to find the mean of those values. And then we want to do that for every month. So instead of retyping this or copy paste and change and blah 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 all that, you don't have to do that. All you have to do is just copy the row that you type and put it into Excel, and then let's say we paste it here, then put all the months down like this, and then just type an equation that says concatenate the characters you want all the way up to where you say the month, then comma, and then you refer to the month, comma, and parenthesis, and parenthesis. Okay, so with that, then all you have to do is just simply drag this down, and it will put all the things in that you need. So then you just highlight all those values, Control C, and go back to your model. We need to be in edit mode. 1 second. Okay, so then you just come back over here, go up to the first cell and hit Control V, paste, and they're all in, and they're all good. So that's a fast way. Typically, we don't use data elements to collect other referenced outputs like this, but in this one case, you should do it, I think, as opposed to using an expression element. Now, you could use an expression element. The expression element would have to be a vector of months, but the difference here would be that you would have a vector constructor like that, and then you would have to paste all those things in with comma separators. So that's the difference. Anyway, now that we have those tables, now all we have to do to build our stochastic element is refer to the mean, average, and the standard deviation for each month. So that's easy enough to do. The other question is, what probability distribution do we want to use? And I looked at a few and kind of had to iterate a little bit manually just to find a good one that gave me a good match. Not a very scientific way to do it, but still I used some judgment and came up with what looks good for now. But this log normal distribution does fit pretty well. We could do some additional analysis to zero in on the best probability distribution type. There was another model where we went through that process when we were looking at, it's a model we have in our library for studying streamflow data. You can have GoldSim do that kind of thing, but in the interest of time, I didn't. I just looked at how our wind speed compares to the measured wind speed over many realizations, and looking at different statistics, and landed on this one. Ideally, what you'd want to do is actually compare this distribution. So compare this shape to that of what we generated from the submodel. We could do that quite easily, actually. But anyway, okay. What we want to do then is so we define the distribution using those values that we got out of the submodel, right? All based on historic records. And then we have to resample it, and we'll just do that every day. I also put some correlation, some autocorrelation, which I'll talk about here in a second. Let me run the model. So we run the model, and then we look at the time series, and you can see the stochastic is what GoldSim is generating. The green is what is historic record. So it's not perfect, but you could flip through the realizations. You could look at some of the statistics and see that those match pretty well. And so anyway, this is just one realization, one of many that it might generate. But it's not too bad, and the mean value matches, the 90th percentile matches pretty well, and the 10th percentile matches pretty well. So it looks pretty good. It could be probably improved a bit, but still gives a pretty good model of wind speed, I think. And so then all you need to do is just supply it with a historic record, and then you can run as many future projections as you want. Okay, so let me just talk a little bit about autocorrelation now. If you zoom into any part of this model, you'll see that there is a little bit of a trend in time, sometimes, not always. But if you have you see a lot of times where there was a higher than average wind speed, and it stayed higher than average for a while, and then it drops below, and it stays below for a while, and then it comes back up. That kind of a pattern where you have some little bit of memory where it kind of stays like that, we can replicate that with autocorrelation, because what it does is on our subsequent sampling that we do, let's say on the next time step, it will correlate where it samples in the distribution to what it sampled on the previous time step. And it's not exact if you don't put a correlation factor of 1.0. That would be a perfect correlation, therefore it probably would not change. But if you if you go down from 1, you start to approach 0, you get less and less correlation until at 0 there is no correlation in time. But anyway, so with a small amount of correlation and a log normal distribution as the assumed inputs that we need for this, not necessarily backed up by anything, with those two assumptions and our historic record, we can generate pretty decent wind model going forward. Okay, so that concludes today's presentation. We talked about incorporating temperature, radiation from the WGen model, how to develop them, how to run it, and also we talked about how to model another type of input parameter that you might not have a model for, but you have historic records. You want to do a statistical analysis and use that to generate values stochastically. You can do that too in methods like this. So I hope this is useful, and it will lead into our next lesson on evaporation and evapotranspiration. So I hope you can make it next week as well. Thank you for joining, and I will be posting this recording. And right now I'll just wait to see if there are any questions. If not, thank you very much, and see you next week. Someone asked, I didn't know it was possible to get the average value of a variable during periods. Well, actually, you can do this with reporting periods very easily, if that's what you're talking about. So like, for example, this expression element, well, this expression element right here is actually doing something a little bit different. Yeah, this is just grabbing those values, but we could use the reporting periods to get monthly and annual averages of this output, of any output, any daily output in your model, well, any hourly, and it doesn't matter the time step. But the point is, you could turn on reporting periods and get those in your charts immediately without doing any extra work besides just configuring it, configuring your chart to look at those reporting periods. So yeah, you can look at cumulative, you can look at average, you can look at the end value, and you can even plot all values to compare all values to reporting values. So yeah, you can do it that way. You can also do it this way that I did it, but this is different because we need to use the values. We need to use the average values, and that's the difference. So it depends on if you need to use them or if you just need to view them. If you're viewing them, It's just a matter of reporting periods. If you're using them, then you have to calculate them in some way. And in this case, I wanted to get a distribution, in not just calculate the average. I wanted more than that. I want the entire distribution, and so that's why I sampled all the values. Okay, so somebody asked, can GoldSim can know somehow when the tendency changes? So until the change, the model gets the average. Um, let's see, and then calculates another average. Yeah, that's true. That's true. Okay, so I think what you're talking about is running average, and yes, we could calculate running average too. What we're doing in this model though is we're doing a pre-process. We're doing something at the very beginning of before at time zero. We do a whole bunch of calculations at time zero, and that's all done in the submodel. So I should probably show you when the submodel is triggered. By the way, I guess I didn't show you that, which I should have. But in the submodel, there's a triggering mechanism. If we open that, it shows here that it's auto-triggered when the model activates. That's time zero. But we've added an additional constraint that it only run on realization one of this outer model. So what that means is it only needs to run once because we just need the data from it. And once it's done, we don't have to repeat any of the calculations, which is nice. So what that means is at time zero of this main model, we've already developed all of the averages, all the standard deviations, all the probability distributions from that entire time series before we even start the model. This is all at time zero. It figured those out. Then we run through the model using that information going forward from time zero onward using the stochastic. So it's a totally different way of calculating averages. There are lots of ways of calculating averages. You can do it on the fly as you go if you need. Then it's changing as you go, like a running average. You can do it that way, but it just depends on your needs. What we have here, we needed the information before we start time in the simulation. We need the information at time zero, all of it. And so that's why I did it this way with the submodel. I hope that makes sense. The submodels are they can be very complicated. They can make a model very complicated, and it can be difficult to describe because it's actually a model. It's another GoldSim model inside of your model. And interestingly, some people put those inside of submodels. They have nested submodels inside of submodels, so that's even more confusing. I try not to do that very often, but every once in a while it's needed. All right, if there aren't any other questions, I'll go ahead and close this up. Thanks a lot for joining. See you next week.